Hello, and welcome to Astronomy Needs You from the Open University. Today, we're going to have a discussion and answer some of your questions about a big change that's coming in astronomy in the next few years. This threatens to overwhelm us with new data, and we're going to have a discussion about what it is we're doing to prepare for that and how it is that you can get involved and why we need your help. Throughout our discussion today, we're going to talk about some websites and videos, and there's more information that you might like to check out on our website and links to the things that we're going to talk about at superwasp.org/British Science Week. My name is Adam McMaster. I'm a second-year PhD student here at the Open University. I'm using citizen science, that's help from volunteers like you, to work through data from a survey called SuperWasp. SuperWasp was a ground-based search for exoplanets, that's planets around other stars. And it was actually the most successful ground-based search for exoplanets. It ran for over 10 years and finished a few years ago. And what we're doing is repurposing the data from SuperWasp to look for new things. Specifically, we're looking for black holes, and we're going to talk a lot more about that today. And I'm also looking for variable stars, which we won't have time to talk about today, but you might like to check that out later. Variable stars are stars that change in brightness, and one of our projects linked from our website deals with that. Joining me today are Professor of Astronomy Stephen Serjeant, Lecturer in Astronomy Hugh Dickinson, and Postdoctoral Research Fellow Beatriz Mingo. Would everyone like to just say a few words about what it is that you work on? Stephen?
Okay, hi, I'm Stephen Serjeant. I'm an astronomer at the Open University. I am particularly interested in galaxies in the early universe and how they form their stars. I'm interested in gravitational lensing as well. This is where you have two objects roughly lined up along your line of sight. You've got a foreground one and a background one. And you're seeing the background one through the warped space-time that surrounds the foreground one. And this makes very pretty arcs and pretty shapes when you see galaxies lined up like that. And it also happens within our own galaxy. So you can have two stars that are lined up, or a star and a black hole. And that's the sort of thing that we're going to be examining in today's citizen science experiment.
Great. And Beatriz.
Hi everyone, my name is Beatriz Mingo, and as Adam said, I am a postdoctoral research fellow here at the Open University. My work is on supermassive black holes, which are kind of the big cousins of the ones we're going to be hunting today. And most of my work involves data from radio and X-ray telescopes. In radio in particular, I work within the LOFAR collaboration. LOFAR is a network of European low-frequency radio telescopes, and it's one of the precursors to the square kilometre array that we're also going to be mentioning today.
Great. And Hugh?
Yeah, hi everyone, my name's Hugh. I'm an astronomer here at the Open University as well. I work with Adam on the SuperWasp Black Hole Hunters project, but in my everyday job, I'm a bit like Stephen. I'm interested in studying distant galaxies in the universe, and in particular how they form their stars. But I'm interested in a quite unusual type of galaxy called the clumpy galaxy. And because those galaxies are so unusual, particularly when we get into the universe that's a bit more nearby, we need to use really big surveys of the sky to try and find lots of examples of these galaxies. And when we do that, we generate huge amounts of data. And one of the big challenges that I have to deal with in my job is how we process those data to try and extract the scientific information that they contain. There's a couple of ways that we do that. One of the ways, which we'll be talking about a lot today, is with citizen science. So that's inviting members of the public to look at these images of space and tell us stuff about them. And another thing that we do is we use machine learning, sometimes called AI, which is where we try and get computers to do very sophisticated tasks, not by programming them exactly how to do the task, but by making them learn from the data themselves what the interesting patterns in those data are, so that we can hopefully get some scientific insight from them.
Great. So, as I said a moment ago, there's a big change coming in astronomy. It's really what we call the big data revolution in astronomy, where a new generation of telescopes is about to come online, and some of them are operational already, which are going to produce a huge quantity of data we need to figure out how to deal with. We've got telescopes such as the Vera Rubin Observatory, which is currently under construction in Chile, and should hopefully start operating later this year. There's the Gaia Space Telescope, which has been operating for a few years and is just about, in a few months, it's just about to do its first full, really complete data release. And also in radio astronomy, there's the Square Kilometre Array, which will be a network of radio telescopes, will be built in South Africa and Australia. These telescopes and ones like them will produce more detailed measurements of more objects in the night sky than we've ever had before. So much so that our current techniques for dealing with data are going to struggle to keep up. We're going to need new techniques such as machine learning or artificial intelligence to allow us to process that data. Unlike today, we won't be able to simply come up with new methods and new algorithms to look for each thing that we're interested in studying. And that's where machine learning can help us, because machine learning can help us find new things just by teaching a computer from examples. In order for that to work, though, we need people to label those examples to start with so that we have the labeled training set that the computer can learn from. And that's where volunteers like you come in. The Open University recently produced a series of videos introducing the idea of machine learning called 60-Second Adventures in Artificial Intelligence, and it was narrated by David Mitchell. We're going to watch the third video in that series, which introduces the idea of how citizen science projects can be used to train machine learning algorithms, train computers to solve new problems. There's a whole series of these videos, so you might like to check out the rest later, and you can find links to all of them at superwasp.org/British Science Week. For now, though, we'll just watch the third video in that series, which is Humans Teaching AI. I'll just share my screen to play that. Here we go.
"60-Second Adventures in Artificial Intelligence, Chapter 3, Humans Teaching AI. Though they've got intelligence in their name, AIs are born stupid and learn slowly. AIs need to be shown masses of example data, while humans can learn their skills from just a few examples. But once they've finished learning, AIs can be impressive. Recognizing a cat would be relatively easy for an AI. The internet has millions of cat pictures because people just love cats. But when AIs look at something rarer, like a green pea galaxy, the data just isn't available, which is where citizen scientists come to the rescue. Because humans are good at identifying unfamiliar things, thousands of volunteers and researchers can look through data online and label items that the AI doesn't recognize. And once the AI has the correct data, it can get on with its work. Until the next time it needs some help. To find out more about how AI is helping scientists understand the universe, visit projectescape.eu/AI.
So that's roughly how citizen science can be used to train machine learning. And we're going to talk a lot more about that in a little while. So at the Open University, we run quite a few astronomy citizen science projects. Today, we're asking for your help with one specific project called Black Hole Hunters. In this project, we're looking for black holes. Those are the ultra-dense remains of dead stars. And the ones we're looking for are more or less completely invisible. As you might expect, that makes them quite hard to find. But luckily for us, these black holes orbit other stars, which are stars that we can see. Also, luckily for us, sometimes when the black holes and the stars are lined up just right so that the black hole passes between the star and Earth, the black hole's gravity can act like a lens and magnify the light from the star, which produces a peak in the star's brightness, giving away the fact that the black hole is there. So your task today is dead simple. What we need you to do is look at graphs of how bright different stars are over time and look for those telltale peaks in brightness that might mean that there's a black hole there. Let me show you how that works. If I share my screen again. Which window do we want? This one. So this is the Black Hole Hunters homepage. You can see it's available at zooniverse.org, and you can also find a link to the project at superwasp.org/British Science Week. And there's lots of information about the project here. There's some recent discussions and some statistics here. You can see it says the project's at 98% complete. The project's been running for a few months and has already completed a large amount of data. The 98% is a little misleading because we have a lot more data queued up ready to go. It's just not reflected in these numbers just yet. And there's some more information about the project here and some more information in the links. But what we're going to focus on today is the classify page, which you can find from this link at the top here. You can also click on this big yellow find a black hole button, and that'll take you to the classify page as well. So when you click through to the classify page, the first thing you see is a tutorial here, which you might like to read in your own time. And once you close the tutorial, on the left-hand side here is a graph of the brightness of one particular star over time. And you see that there's days along the bottom here and a measure of brightness up the side. And then there's one simple question that you need to answer about each graph. Can you see a sharp peak in the graph that might be a hidden black hole, yes or no? So the first thing you might notice about the graph itself is that there are two kinds of markers on the graph. There's these white squares and there's also red circles. The white squares are individual measurements of how bright the star was, and the red circles are a daily average of those measurements. It's mainly the red circles that you need to pay attention to. Those give you the best sense of the overall shape of the curve, of how the star's brightness varied over time. And the white circles are useful for gauging sort of how noisy the data is. And what you're looking for, this is a good example here actually, what you're looking for are peaks like this in the star's brightness that stand out above any noise and above the background level of fluctuations. No star is completely constant in how bright it is. You can see there's some variation over time for every star, but we're looking for distinctive peaks like this that are symmetrical so that they look the same on the left as they do on the right-hand side. So let's look at a few more examples of these. Oh, I should say that we're looking for ones that have, well, 4 or more red circles. You can see here it says we're looking for symmetrical peaks that contain 4 or more red circles. That's so that we can be sure that the event isn't too short to be a black hole. So the events we're looking for should last a certain amount of time. And if you remember that each red circle is 1 day's worth, it's an average of 1 day's worth of measurements. So 4 or more is sort of the threshold for where we think that's long enough that it could be one of the black holes that we're looking for. So we'll look at a few examples now to give you an idea of how this works. As I said, this is quite a nice example of a potential lensing event. So we'll say yes to that one. You can see there's a peak here. There's maybe 4 or 5 red circles in that peak, so we'll say yes to that. This one doesn't look so much like a lensing event. You can see there is some variation in the brightness. All stars have that. There's nothing that really stands out above the background noise, so we'll say no to that one. Oh, that's an interesting one. So here you might say that looks like a peak, but in this case there's actually only 3 red circles there, so we can't really be sure that this is a potential lensing event. It's probably too short. I mean, there are some gaps in the data, which happens sometimes as well, but I think for this one, I would say no, because there aren't enough red circles. And that's a nice one as well. So you can see here, there's quite an obvious peak here. There's quite a big gap there, but you can still tell there's a peak. So that's a yes. And so on. There's one other example that I do want to show you, which was this one. Sometimes you'll see a peak that doesn't quite fit into the range of the data that we're looking at. So you can't really tell that it's symmetrical, but I would still say yes to this one because it is quite an obvious peak. The shape looks about right. So if you see one that's sort of on the edge of the time window, that's still a yes. Don't exclude those ones. So we'll say yes to that one. So, as I said, you can find the project at zooniverse.org, or you can also go to superwasp.org/British Science Week and follow the link from there. So, throughout our discussion today, we're going to check in on your progress and see how well you're doing on the project. What we want you to do is just do a few classifications here or there while we're talking. As you just saw, each classification doesn't take very long. So if you just do a few at a time, very soon between the group of us, it should add up to quite a large number of classifications. And do remember that more than one person is going to see each graph. It doesn't all come down to your individual answers. So don't worry about making a mistake. If you do make a mistake, other people will catch it. If you're not sure about something, just make your best guess. You don't have to get everything exactly right. When the project's finished, we'll put everyone's answers together and come up with a consensus answer for each light curve. So let's have a look at how things are going so far. I've got share my screen again. So this is our dashboard showing our progress today, and we can see that there's already 178 classifications. That's really good. And on the right hand side, you see there's this measure of agreement. And now what that means, that's a measure of how well each individual's answers agree with the consensus for each star. We thought this would be a fun way of measuring how well we do today. Ideally, this number should be as high as possible. You can see when there weren't so many classifications before people saw where the project was. So there were 0 classifications until I showed people where the project was. Then we've got some classifications coming in now. So ignore this 100% part here, but the agreement measure is starting to go up again now, so that's good. Ideally, this number should be as high as possible. So our goal today is to get both of these numbers as high as we can. We want to do as many classifications as a group as we can. Ideally, we want to try and get the agreement as high as we can. If everyone's being as accurate as they can, I think we can get that number quite high. Though 94% is a pretty good starting point. So we'll check back in on this periodically throughout the next 45 minutes, and we'll see how everyone does. So let's get started with our discussion. Whether you're watching on Facebook Live or on YouTube, you can submit questions for the panel via the chat box. Just write your questions in there, and they'll all get fed back to me, and I will pass them on to the panelists, and they can answer them for you. While we're waiting for the first questions to come in, though, I'll ask the first question, and we're going to start with the most basic question about black holes, which is, what are they? What are black holes? Stephen, could you answer that for us?
Oh, okay, yeah, sure. So a black hole is it's an object which is so heavy that light can't escape from its surface, so it appears black. And one way of creating an object that's so dense that light can't escape is to take matter and crush it down into a really small space. So, for example, you could take planet Earth and crush it down. It'd be pretty bad if you were living on planet Earth, but you could crush it down to, I don't know, the size of a marble or something. And that would be dense enough for light to be unable to escape from its surface. And so it would be black. And because nothing can travel faster than light, that means stuff is trapped inside this black hole. And when you talk of black holes in this way, it tends to suggest that you need extreme crushing to make a black hole. And the funny thing is it doesn't have to be the case, because if you, for example, just filled this entire solar system up with tap water out to, I don't know, the asteroid belt or Jupiter, right, out to the radius of Jupiter, that would be enough mass in one place to prevent light from escaping from the surface. So that would form a black hole. So you don't necessarily need extreme crushing to create a black hole. You just need enough matter in one place to prevent light escaping. And that black hole turns out to be a supermassive black hole, like you find in the centers of galaxies. Also, there's not enough water in our galaxy, not by a very long way, to do this. So don't worry, the apocalypse is averted. But that's how you do it. You just need enough stuff in one place. and then light can't escape. And then, because nothing can travel faster than light, everything is stuck there. And so you fall in, that's it. It's a one-way trip.
Great. So you need enough stuff in one place. What are some of the ways that that stuff can get in one place? Where do black holes actually come to? Beatriz.
And this, we think there is one key way in which black holes form, which is through the collapse of a star. I mean, it's the best way in which you can put a lot of mass in a small space. You essentially burn it for a while during the lifetime of the star. And at some point, when the star runs out of the type of fuel it needs to counteract this push, this crash from gravity, it is a push, it's a crash. It's just done by gravity itself. It's just pulling things in. The star, while it's working, when it's burning helium and hydrogen, carbon, neon, oxygen, in the early stages of its life, can counteract this pull. At some point, it runs out of enough fuel to counteract gravity, and it collapses. And if you have a large enough amount of gas in that star, if you have something that starts from around 10 to 20 solar masses, you end up with a black hole. If you have something smaller, something like our sun, for example, you form a white dwarf. And if you have something a bit bigger than our sun, but smaller than what forms a black hole, you end up with a neutron star. So that's what we think that is a key way to form a black hole. Obviously, that you have, stellar black holes, which are the ones we're working on today. But you also have heard, as mentioned, supermassive black holes, like the one we find in the center of our galaxy and indeed in the center of most galaxies. And those, we think, work through mergers of smaller black holes. So that's the other way to form larger black holes. Essentially, you can grow them through, throwing gas into them, or you can merge them. There is a bit of a conundrum with how big supermassive black holes have grown throughout the history of the universe. So there is a hypothesis that says that we actually form black hole seeds in the very early universe. We haven't been able to prove or disprove that. It's just one of the ways you can get to form such a big amount of mass in the center of a galaxy in such a short time, relatively speaking. And it's one of the things we hope to solve with the next generation of telescopes.
Great. So we've got a couple of questions coming in about the citizen science aspect. So let's come back to black holes in a moment. We'll tackle these questions first. So our first question is, do you know of some interesting discoveries that were found through citizen science projects in astronomy? Who wants to tackle that? Hugh, you haven't answered anything yet. How about you start?
Sure, yeah. So I know of a couple that are really interesting, not from black hole hunters, but from a previous project called Galaxy Zoo, which you may have heard of. The first one of those is something that was discovered by a Dutch, well, not a Dutch astronomer, a Dutch citizen scientist, as it happens. And they were looking at an image in Galaxy Zoo, and they were looking, first of all, they were doing their job. They were looking at the galaxy in the middle, and they were classifying it and doing a fantastic job at that. But then they looked a little bit away from the center where they'd been told to look, and they saw this sort of weird green glow. And what on earth is that? One of the great things about Galaxy Zoo is it's not just a platform where you can go and do what you're told. It also has a forum attached to it that we call Talk. And so what this person did is they went to Talk and posted and said, I've seen this really weird green thing in this image. Does anyone know what it is? And even the astronomers actually didn't really know what it was. So that sparked a whole strand of investigation to try and work out what this thing was. And it turned out it was actually the remnant of an old radio outflow, a little bit like the things that are behind Beatriz, actually. So that's one thing that was discovered completely serendipitously, by accident, by luck, in Galaxy Zoo. A second thing that was discovered, also green, keeping on the green theme, was a special type of galaxy called the green pea galaxy. And we heard about those actually in the video at the beginning of this presentation. So what's a green pea galaxy? A green pea galaxy is a galaxy that's really small and is forming stars at a really high rate. And the reason it looks green is not because if you looked at it with your eyes, it would look green. It's because of the choice of filters that we put on our telescopes to filter out the light so that we can make the color images. Now, again, this is something that professional astronomers just weren't expecting to find in the images. They thought they knew what galaxies looked like. They thought they'd be red and sort of oval shaped, or they'd be these lovely spiral galaxies that we're all familiar with. What they didn't expect were small green dots that look like peas. And again, these were discovered completely by accident, just by volunteers, citizen scientists, looking at the images, spotting something that looked a little bit strange, and telling the scientists about it.
Great. And we've got another question here about citizen science, which is, when classifying, do you capture the time it takes a person to make a decision? I think that if the time is longer, the person is clearly not sure. So you could feed this uncertainty into the data. Who'd like to answer that one? I'll pick someone. Stephen?
Well, I would say yes, you could. Whether we do that in all of our experiments, I don't know. Are we doing it in our current experiment?
Hugh, did you?
No, we're not doing it in black hole hunters. I think it's one of the things that gets done to see if it works, and actually it turns out that in general it doesn't really work, because people do citizen science projects for different reasons. A lot of people do it because they want to learn about science. A lot of people do it because they want to contribute to science. Some people do it just because it's fun, and if they're really enjoying looking at a picture of a galaxy, it doesn't necessarily mean that they don't know what it is. It just means that they really like the picture. So you could be misled if you were relying on timing information like that.
That's interesting. So let's come back to black holes for a minute. What are some of the ways that we can detect black holes? I said that the black holes we're looking for are almost completely invisible. Other black holes are detectable, though. How can we find those? Beatriz, can you?
Well, we can detect even invisible, ninja black holes, just because of the effect they have on their surroundings, not just through gravitational lensing, but for example, we can see, quote unquote, the black hole in the center of our galaxy through the orbits of the stars around it. We know there's something we cannot see in the middle, but it's tugging at stars, and we can see the motions of the stars through decades. Eventually, we just follow them with telescopes for years and decades, and we can see that they trace orbits. And then we know that there is a big mass there that we cannot see. But we also can detect black holes which are active, what we call active galactic nuclei, for example, or in the case of stellar black holes, we can see them in X-ray binaries. That's when you have a black hole with a companion star that is seeding mass. So when you have a black hole that is eating, exactly like that image there, when you have a black hole that is actively eating gas, not all of the gas makes it to the center. And even the gas that does make it to the center, as it orbits around, essentially, it heats up through friction, same as you would heat up a piece of metal by putting it in a furnace, for example, or with a torch. And it starts glowing, it starts red and then yellow and blue eventually when you get it hotter. The gas around these black holes also heats up and starts brightening up in shorter and shorter wavelengths of light. As it gets hotter and hotter, and it emits a lot of radiation. So these are some of the most luminous phenomena that we can see in the universe, in the case of the ones that are in the centers of galaxies, and even the ones in X-ray binaries we can detect from very, very large distances, because they are so incredibly bright. So we can see them through light, and we can also see their effects on their surroundings. As I was saying, not all of the gas falls into these black holes. We can generate winds, and we can generate jets from the vicinities of these black holes. The thing you see behind my head is actually one of those jets that travels through distances that are hundreds or thousands of times larger than the galaxy itself. This is Hercules A. You can see. Thank you, Adam, for sharing this image. So the central galaxy you can see there is kind of yellowish with a bit of a haze. That's a massive elliptical galaxy, much larger than our own. And the tiny black hole in the middle is emitting these very powerful jets of plasma, of very, very hot gas that can travel enormous distances, just far, far beyond the host galaxy. And we need all sorts of funky physics to study that effect. But we can see this obviously very, very far away, up to almost the dawn of the universe.
So, as you said, we can see black holes through their effects on their surroundings. The black holes we're looking for today are visible because of gravitational lensing. So how does that work? How is it that a black hole can magnify the light from another star? Hugh, why don't you take us through that?
Sure. So imagine that the star is just sitting there by itself to start with, and it's radiating its light out in all directions, and it's sending these rays of light out, and they're basically traveling in straight lines. And so when we see a star, we see a small amount of the light that has come along a straight line from the star to us. Now, if we're really lucky and a black hole happens to be passing almost directly between the star and us, the black hole, as Stephen mentioned, its gravity is so strong that what it actually does is it changes the shape of space, a bit like what this video that Adam is showing, changes the shape of space so that those straight lines, they now look bent. And so what happens is a little bit of that light that would have gone off somewhere else, it wouldn't have made it to our telescope. Instead of going on the original straight lines it was on, it travels on these lines that are now bent and comes to our telescope. And so we see a little bit more light than we would have done before. And that creates this distinctive peak that you're hopefully all now searching for in Super WASP black hole hunters, and that you can see in the bottom right-hand corner of this screen. Does that answer the question?
Yeah, I think that does. And we've got a few questions about black hole hunters now. So first question here, do the relative velocities of the star and the black hole impact the data set? So does it matter how fast the two are moving? Hugh, I think.
Do you like me to answer that?
Yeah, I think
yes, it certainly can do in a couple of ways, actually. Obviously, if the black hole and the star are basically in an orbit that's very, very fast, then the black hole will fly in front of the star. And because we only have really day time scales, we would miss that. We're asking you to look for something that lasts about 4 days. But the other reason is that lensing effect actually depends quite a lot on the geometry of the system. So there has to be a certain configuration of distances between us and the black hole and the star in order for that lensing effect really to work. And it turns out that when that geometry is right, when those sets of distances are right, there's only a certain set of actual orbital radii that work for that. And so it's actually quite unlikely that we would see a lensing from something that was whizzing around its star really, really fast. And it's also very unlikely that we would see something from a black hole that's very, very far from its parent star. So we're really looking for a set of orbital systems where the periods of the black hole going around the star, they're somewhere between 10 to 100 years. And that means that we're only going to see them once in the Super WASP black hole hunters data set, which is what makes them really difficult to find, and which is why we need your help.
So there's an interesting question here. The signals in the project can be from different sources, not just star black hole interactions. So how are the signals attributed to certain specific interactions? And I've got a related question on my list, which is there anything else that can cause the lensing effects that we're looking at? Stephen, why don't you tackle this second part? What else can cause lensing effects?
Well, they could be passing objects. So we're imagining that there are black holes and stars in orbit around each other. But it is conceivable that you could have something just floating through the halo of our galaxy and going past and just happening to intersect a star. Now, it's much less likely, I think, but I mean, it's a physically possible thing. And in fact, the first time the sort of stellar lensing was discovered, that was with objects floating through the halo of our galaxy. So that was it's called gravitational microlensing, and that was well, it was one of the first insights we have to the nature of this unseen component of matter, or dark matter in our galactic halo. It can't all be black holes, it can't all be Jupiters floating around, it can't all be white dwarfs or whatever, but clumps floating around the halo of our galaxies is certainly one thing that can and has created these microlensing, these gravitational lensing effects. And again, they will be just single events, they won't repeat as well. The other thing that I guess could cause fluctuations in the light curves is something going on within the star, but you wouldn't expect those to have this beautiful symmetry. So those are the sorts of false positive events that you want a citizen scientist to look at the data and say, yeah, that doesn't look quite right. I don't quite. It doesn't look symmetrical enough. And it's very difficult to automate that because the data is patchy, as you'll have seen looking through the data. So it really does need a human being to come to an assessment as to how symmetrical the effect is, and to rule out something going on within the star.
Great, I think you answered both parts of the question. That's good.
All right.
So let's have a quick update on how the project's going so far. We're getting a good number of classifications in. So I'm going to look at the dashboard. So we're already at 2,800 classifications, which is fantastic. The agreement measure, I think, is just leveling off. So that's good. I think that's settling into the real agreement value that we're getting. I think when we have a small number of classifications, the agreement can fluctuate quite a lot. So I suspect we hopefully might see the agreement start to go up in the remainder of our discussion today. But that's great work so far. Wow, okay, that's just jumped up to 2,949 classifications as I was talking. So that's quite a good rate of classification. So good work, everyone, so far. Let's keep that going, and we'll check back on this again in a few minutes. So there's a general question here about citizen science and how people can get involved. So is there a way to help that's not just through citizen science projects? Like, do you need people to write code and that sort of thing? Beatriz, maybe you can suggest some ways that people can help, maybe.
I mean, yes, we need all the help we can get. And in fact, there are always jobs associated, technical jobs associated with any telescope you plant anywhere. We are the visible face of the science process, us scientists writing papers and talking to the public and giving interviews and stuff. But there's a huge number of people involved in any data that we produce and in any science that we produce. There was actually quite some news coverage, for example, when the M87 black hole shadow was shown, just citing how many hundreds of people have been involved just in the research. Imagine how many more people were producing the software and maintaining that equipment and just keeping us going, essentially. We are also depending on admin, on buildings, on maintenance stuff, etc. So doing the science is one of the jobs, but even just the technical side of developing code and maintaining the systems and sustaining this process takes a huge amount of people, and those jobs are coming up constantly. So if you have that sort of background and you're interested in applying for these things, there are things like space jobs, for example, or in space careers. There's a website that you can look into for things that are perhaps more related to space. Jobs.ac.uk has listings of jobs related to astronomy and related to university work, even admin work that is absolutely necessary. Science communication jobs. Absolutely, there's many ways to get involved with science without being a scientist, and we need all of you.
Let's talk more about citizen science and what it is we're trying to do with it. Hugh, can you talk about some of the things that we're hoping to apply citizen science results to in terms of machine learning and methods like that for processing our data?
Right. Well, okay. Let me talk about the science first, and then I'll talk a little bit about the techniques as well. So, as I said a little bit at the beginning, one of the things that's coming around the corner and making us all a little bit nervous, if we're totally honest, is these huge surveys that are going to be producing a deluge of data that's got this exquisite quality and just absolutely huge volume that we're really not very used to dealing with. And so what we're going to need to do is come up with some way to automatically analyze those data, because they'll just be far too much for even a huge group of citizen scientists to process. But at the same time, we want to make sure that our analyses are, first of all, accurate, and secondly, that we're not going to miss anything that's really interesting. And so what we would like to be able to do is to make an automatic algorithm that behaves a lot like a human being. So this is an algorithm that can do the job well, but will also spot those odd little things in the corner of the image that we weren't expecting to see it and let us know about it. Now I'll start to talk a little bit about the technical side of stuff. Now, the problem with automatic algorithms is that, well, until very recently, scientists basically had to know in advance what they were looking for. And so they would sit down at their computer and they would make a program and they would tell it exactly what to look for. And they would analyze the data very quickly and it would work. But it would only tell them what they already knew they were looking for. Very recently, there's been a development called machine learning, or sometimes called artificial intelligence, where what we do, we don't tell the computer program exactly what to look for, but we give it a load of data that we already know the answer for, and we say, this is the sorts of things that we're looking for. Can you find things in the data set that look a little bit like this? And that works really, really well if you've got lots of examples of things that you want to look for. So going back to the video at the beginning, the internet is full of cats. So it's really easy to train a machine learning algorithm to find cats in pictures. However, when it comes to astronomy, we don't have lots of these examples, what we call labeled training data for our machine learning. And so one thing we could do is we could get all of our PhD students to sit down and make labels for all of these data. And Adam would love that, I'm sure. But what turns out to be a much better idea is actually to use citizen science. And that's for two reasons. The first one is that there are many, many more citizen scientists and that they can process much more data and generate many more labels. And the second one is, it turns out that even Adam makes mistakes, okay? So if we just get Adam to go through 10,000 examples of galaxies, he's probably going to get 5% of those wrong, okay? If we ask 30 volunteers to all look at 10,000 galaxies, those same 10,000 galaxies, some of them might get them wrong. They may even get more wrong than Adam, although who knows? But when we take all their results and put them together, aggregate them together, the result that we get on average turns out to be extremely accurate. And that's one of the great advantages of doing citizen science. So once we've got these labels from citizen science, then we can use them to train our machine learning algorithms. And I will say one more thing. There's one more really interesting thing that we're trying to do at the moment, is that we can now build machine learning algorithms that have some idea of where they're not sure about the answer that they're giving. And so what we can do is we can do something called active learning. And active learning is where the machine learning algorithm says to itself, well, I'm not so sure about this particular label that I've assigned to a source. I will ask the citizen scientists to give me the label that they think. Then I will take their new label on board and I can use that as training data to improve my future predictions. And that's one of the really exciting things that we're trying to do at the Open University, and actually astronomers all around the UK are also trying to do.
Great, thank you. We've got a couple more questions about black holes. So Stephen, I'll pass this one to you. How can a black hole collapse happen if there is no gravity in space?
Oh my goodness, that's a really good, really deep question, actually, because you see videos of astronauts on the International Space Station and they're just floating around, right? So it looks like there is no gravity at all. But there is gravity. There is gravity in space. So the reason that the astronauts don't seem like there's any gravity in the International Space Station, the reason why the astronauts are floating around is because the International Space Station is falling. It's in free fall. So if you built a tower out to the huge Tower of Babylon, right out to the height of the International Space Station, and stood on the top of the tower, you wouldn't be floating. You'd still be feeling gravity. But the International Space Station is dropping. Now, the reason why it doesn't just drop and just land straight on the Earth is because it's also going sideways really fast. So it's falling towards the Earth, but it's going sideways so fast that it keeps missing the Earth. And that's actually what an orbit is. It's just continually falling. And this is actually, this goes down to a really deep principle in Einstein's theory of gravity, is that when you're in free fall, when you're falling, you don't feel gravity. And that's a really fundamental part of Einstein's theory. And this is why this question is a really good, really deep question, because it seems like there is no gravity in space, because you just see the astronauts floating, but the astronauts are falling. But there are still things in space, and these things have mass, and these things pull stuff. So there is still gravity in space. It just so happens that the pictures that we see wipe out the effect of gravity. Really good question.
So we talked about black holes forming from collapsing material under gravity. Beatriz, can you tell us a bit about how supermassive black holes form? Is that similar?
As I said earlier, we can potentially form supermassive black holes in the early universe just by direct collapse as well. This is a theory. This is not something that we have been able to observe yet, partly because the very early universe is something that is very, very difficult to observe in all the terms. It's not really transparent to light before what we call the epoch of reionization. So we cannot actually see with light anything in the very, very early universe. Past that point, the signal is very weak, obviously, because it's our photons that are coming from very, very far away. But this is something that we hope to explore with the next generation of telescopes. So at this point, this is a theory that would explain why supermassive black holes grew so quickly, that we can already see them in the early universe having very large masses that we wouldn't expect to have just by adding individual stellar mass black holes, merging them into each other, or just by having them sitting there accreting gas from those early proto-galaxies themselves. The key problem there is that the very early universe had very, very different physical conditions to our current universe. So even the stars behave very, very differently. And you could potentially form stars with humongous masses that you wouldn't be able to do today, that you wouldn't be able to see today. So it is very possible that the stellar mass black holes you formed in the early universe were actually a lot more massive than the ones we see today. And through aggregating those and through throwing gas into those, you might have been able to just form supermassive black holes and eventually move them to the centers of the galaxies, just through mergers and accretion, which is what we see today at a different scale, obviously.
Great. So there's a couple more questions about black hole hunters. First question for Hugh. When can we expect the first results to come?
Good question. Put me under pressure. Hopefully very, very soon. Both Adam and I are working on this at the moment. We've got some nice looking candidates actually, and I have to give credit to Adam. He's working very hard on trying to understand what types of objects they might be. Once we have those answers, we will hope to get those results out to you guys as quickly as we very possibly can. But I gave a great answer there, and I didn't give a time scale. Just really soon.
And then a question about lensing, which I think I'll give to Stephen. If the black hole does not pass directly in front of the star, would partial lensing occur? What would that look like?
Yes, actually, yes. In fact, no matter how distant it is, there'll be a tiny amount of lensing always as the black hole is going past. So it's just the further away the black hole gets, the weaker and weaker the lensing effect is. If it goes directly in front, then you get all kinds of beautiful effects, like multiple. Well, if you could zoom in and see it, you would see lots of pretty patterns, but of multiple rings going round. But even if it's just skirting the edge, it would get a magnification boost. So yes, that's absolutely right. Yeah.
Cool. Let's have another update on black hole hunters, because we've just passed 5,000 classifications now. That's going really well. The agreement is still gradually going down, which I think is probably an indication of how hard some of these light curves are to interpret. I think there's a lot of them are quite quite ambiguous, and that really illustrates why it is that we need human volunteers to look at these light curves, because it's very hard to determine which ones could be lensing events automatically sometimes, especially with data that can be quite noisy. So I think that's what we're seeing now. We're still seeing a really steady stream of classifications coming in, which is great. It's really nice to see this number ticking up. So we've got about 10 minutes left. Let's see how many more classifications we can do. Let's see if we can get over 6,000, shall we? Let's aim for that. I think that's a good goal, nice round number. So we'll check back on that again in a few minutes' time. Let's talk about some of the other citizen science projects that we run at the OU. So Hugh, why don't you tell us about your Clump Scout project and what that's all about?
Sure. So yeah, at the beginning, I mentioned I'm interested in a particularly rare type of galaxy, and I didn't tell you the whole story. Those galaxies, they're not particularly rare in the early universe. Okay, so about 20 years ago now, long time ago, the Hubble Space Telescope was launched, and the Hubble Space Telescope looked out into deep space and looked at some galaxies. And it saw that those galaxies didn't really look like the familiar galaxies that we see nearby. They didn't look like these lovely spiral galaxies. Instead, they looked really turbulent, and they contained these giant clumps of stars, which we call giant star-forming clumps, sort of intuitively enough. And when you look out at the universe as it was roughly 10 billion years ago, you find that 60 or 70% of star-forming galaxies have these big clumps in them. However, when we look closer to us, so when we look at the universe as it is roughly today, that fraction of clumpy galaxies has dropped like a stone. It's basically down at 1 to 3%. And in fact, these images here that Adam is showing you, these are some images of nearby recent galaxies. And these are very rare galaxies because these do contain giant star-forming clumps. And those are the blue blobs that you can see in these galaxies. And so Galaxy Zoo Clump Scout was a project where we wanted to use a very big survey to try and find examples of nearby galaxies that contain giant star-forming clumps. Because if we can find enough of these galaxies and understand the physics that's going on in those galaxies, then maybe we can understand how it is that they became so rare today. Now, one question you might be asking is, why do we care about clumpy galaxies? Well, okay, let's go back to 10 billion years ago when clumpy galaxies were really common. It turns out that that's when the most massive galaxies that exist in the universe today were forming most of their stars, and that includes our own galaxy. So there will be stars in our own galaxy today that formed in these giant star-forming clumps, and we really don't understand how these clumps form, how they behave, how they evolve inside their host galaxies, and then where they went between 10 billion years ago and today. So that's what Galaxy Zoo Clump Scout is for. And the results of that have, in fact, just been published in a paper by my colleagues who work in the USA. And I think you can probably find that paper on the website that Adam has made. And if you can't, we will add the link after this presentation.
Yeah, I don't think the paper link is on there just now, but yeah, we'll add that. We'll add that this afternoon. So another project that we are involved in is called Radio Galaxy Zoo LOFAR. And I think, Beatriz, you've touched on radio jets a bit already today. Why don't you tell us a bit about the LOFAR project and what it's doing?
So the LOFAR project, as the name says, uses data from the LOFAR network of radio telescopes, and the radio universe looks really, really different from any picture of the universe you have probably seen. If you see this galaxy behind me, in radio you only see these extended structures that arise from the central supermassive black hole, but you don't actually see the optical galaxy in the middle. So this LOFAR Radio Galaxy Zoo project is about finding these supermassive black holes, finding where this radio emission is coming from, because that is a task that we absolutely need people for. Our algorithms and our machine learning techniques don't actually allow us to put some of these clues together and to trace the source of some of these black holes. You know, there's some symmetrical arguments we can make based on the shape of these radio emission, but a lot of these sources look wonky and look interesting in various ways. That's where the fun physics happen. So in this example that Adam is showing, you can see, you know, these two radio lobes and a core in the middle where there is some emission as well. But in some cases, we don't actually have that middle piece. So we need people to help us associate these radio components together and tie them to the optical galaxy, you know, the elliptical or spiral galaxy where the black hole is living. This is really important because it's something that we can just about do with LOFAR. It's something that we absolutely won't be able to do with a square kilometer array because it's going to produce such a humongous amount of data that we really need to move on to machine learning and automated techniques. There will probably be some citizen science associated to this, but we absolutely need to learn how to automate things before that happens, because we won't be able to keep up with it otherwise. And understanding that, you know, where these supermassive black holes live, how big these large structures grow, how long they live, is really, really important, because as you can imagine, you know, these vast amounts of gas and energy that is being dumped into very large scales in our universe can have an enormous impact on how the universe evolves and grows. And in particular, this is one of the key drivers and quenchers, essentially, and stoppers of star formation and galaxy evolution. It's also one of the things that we can find in our own galaxy, which used to be active, and we can actually see the remnants, the relics of this radio emission from when our black hole also had these radio jets and lobes, and they likely shaped these are the Fermi bubbles, they're called. This is an artist's impression, but it's just to give you an idea. We can see these relics of two lobes perpendicular to the plane of the galaxy that were likely generated through this mechanism, and that likely influenced the star formation history of our own galaxy.
So what sort of results do you have from Radio Galaxy LOFAR so far? Do you have any?
Well, we're putting all the results together. We will be able to release a catalog that the entire astronomical community is going to be able to use. Essentially, you know, you can have the radio emission, but if you don't know what galaxy it belongs to, there's not much you can do with it, other than, you know, study its shape and you know, do some physics. But to actually understand where it's coming from, you know, how long has it's lived and what impact it might have, you actually need to pull it together with the host galaxy. And I believe that the project is nearly complete at the moment, so we need a few more tens of thousands of clicks. So if it's something you would like to participate on and help us hunt for supermassive black holes, please do, because we really need you.
Yeah, and there's a link to that project on the superwas.org page as well, so people can find the link to that from there. Let's see how we're doing. Let's check if we've got any more questions. So what do we got here? Once citizen scientists identify a potential black hole, do human eyes then verify these candidates, and is there a classification threshold? So Hugh, I'll pass that one to you, if you can give us a quick answer to that one.
Well, yes. Do they get verified? The answer is yes. And I think by human eyes, I mean, they've already been verified by human eyes in the citizen scientists, but I think you mean professional scientists, or we call ourselves professionals anyway. Yeah, we will look at them, and then we will do additional analysis to try and establish whether this really could be a black hole, or whether it's noise or something pretending to be a black hole. So we can do things like we can look in other surveys to see if a similar signal is present. We can do things like taking theoretical models of what the signal should look like and comparing that with the data that have been identified as a potential lensing peak. We can take other types of data and see if we can detect this tiny little wobble in the star that the orbiting black hole would create. There are lots of things that we can do to double check that this is a real signal. The other thing that we do actually on a sort of slightly sideline note is that some of the light curves that we put into the project are actually simulated light curves. We put them in for two reasons, really. One is that these events are extremely rare, and so we need to be able to show you, the volunteers, the citizen scientists, what a real signal would look like, so that you know when you come across a real one what it's going to look like and you don't miss it. But the second one is we can put in ones that are very, very faint lensing events that are basically impossible to see. And then we can slowly build up the magnification in our simulations. And that lets us work out how likely it is that a volunteer is actually going to detect a lensing event with a particular level of magnification.
Great, thank you, Hugh. All right, so we're almost out of time. We just have time for one last update on how the project is going. And I set the challenge of 6,000 classifications. We're actually just past 7,000, which is fantastic. We're still waiting for the agreement measure to level off, but the classifications are still coming in really fast. I think what I'm going to do is I'm going to say, everyone keep this going, keep doing classifications for the rest of the day. And what I'm going to do is tomorrow I will update the SuperWasp website with the results from the day, and we'll see how many we can do in the rest of this afternoon. So do keep going. I hope you've all enjoyed taking part in the project. The work that you've done is genuinely really useful to us, and we are going to use every single classification that you submitted today. So great work, everyone. Thank you so much for taking part and for sending us your classifications, and thank you for watching. Like I said, do check out superwasp.org/British Science Week. We'll post a link to the paper that Hugh mentioned on there, and final results from the day's classifications probably tomorrow morning. So thank you all for watching, and thank you Stephen, Beatriz and Hugh for joining us today, and yeah, and enjoy the rest of your day. Thank you.